Aloha and welcome to the refresher tutorial on the normal distribution. We will be making use of the normal distribution and some of the concepts of it in our Business 631 supply chain management, so it's very important that you have a refresher and fundamental understanding of how the normal distribution works. So to begin, the normal distribution is a probability distribution, and it's a continuous probability distribution. The probability distributions come in two sort of varieties. There's the discrete probability distributions and continuous ones. We'll talk about the differences in a minute. Discrete probability distributions are probably what you're most familiar with, and that's just when we have a finite set of outcomes, and we just like to know what's the probability of each outcome occurring, and the total of all the outcomes occurring, that at least one has to occur, and the probability of any or at least one of them occurring is always 1. The most common discrete probability distribution you're familiar with is the uniform or all equal distribution, meaning that if I have, say, 10 different possible outcomes, then the probability of each possible outcome occurring is 1/10. So you're probably familiar with this from, say, like flipping a coin. Flipping a coin is generally considered to have a discrete uniform distribution where the probability of a heads is 1/2 and the probability of tails is also 1/2. They're both equal. And of course the probability of getting a heads or a tails is 1. No, we don't consider the case where the coin lands on its side as a likely outcome. Whereas continuous distributions are going to be a little more difficult to explain, and where the normal distribution comes in is where we're going to be interested. Of course, there's lots of different kinds of distributions other than the uniform distribution and the normal distribution, but these two are are very common and easy to understand. Now, continuous probability distributions are different than discrete distributions, or we call maybe a continuous random variable, which is that a continuous random variable would be some variable or something value that changes or varies according to that distribution. So a continuous random variable is one that can assume any value on a continuum, sort of an uncountable or infinite number. It's actually more than infinite, but that's a technicality. And usually they represent things like measures, like a thickness of an item, or the time required to complete a task, or the temperature of something, or the height. So anything that is measurable tends to be sort of continuous, and if you're thinking about how the values of that measure can vary, then that would be the distribution of it. So of course, a continuous value is something that can take on any particular value depending only on the ability to measure it accurately enough. So we don't usually make distinctions of just a finite number of things. And sometimes we use continuous probability distributions actually to approximate discrete distribution. We're actually going to do that in our class. You'll see that it's a very convenient thing to do. It's often easier to work with a continuous distribution than with a discrete. Most commonly, we use the normal distribution to approximate the binomial and Poisson distributions. And the reason for that is that the binomial distribution is used for like counting things. Same with the Poisson. They sort of count the number of things occurring over a certain interval. Or binomial would be like counting how many heads you would get in a flip of 100 tosses or something like that. And it's much more difficult to work with the discrete distributions, and there are good approximations using the normal distribution, which are a lot easier, and you'll see that we're going to make use of that ourselves. So let's talk directly about the normal distribution now as a continuous distribution. Now let's a little bit more thinking about continuous distribution. You can think about the distribution as like a bar chart. A bar chart talks about the frequency of, or a histogram of the frequency of occurrences of various different things, like how often does a head occur and how often does a tail occur, or the percentage that it occurs. And a continuous distribution would be kind of like this percentage histogram that we're thinking of with instead of a bunch of bars, what we do is we make those bars get smaller and smaller and smaller. The width of the bars get really small. Or if you look at the histogram of something, you look at the interval getting smaller and smaller. So you keep getting them smaller and smaller and smaller until you can see that you kind of get a nice smooth continuous curve here. So if you look at the distribution of the squares here, you see that it's all jaggedy, but as the width of the intervals of the bins get smaller and smaller, they become closer and closer, approximately like the curve there. And that's kind of what we mean by a continuous distribution. We really mean that this curve here is sort of in the limit. What we talk about a continuous distribution, we generally mean an a priori probability. And what we mean a priori probability is that we are talking about based on sort of knowledge or structure. It's like in theory that this is the way it should be. So we don't necessarily, whereas an empirical probability would be based on what we observe, an a priori would be developed on principles. So, in principle, in practice, there's no such thing as really a continuous distribution. Pretty much anything that we can observe or interact with would not be continuous, but oftentimes we can approximate them very well, or a priori in principle, by a continuous distribution. The hard part about continuous distributions, unlike discrete distributions, is that when we want to know the probability of something, we tend to have to know about the area under this curve. So we don't just add up the number of boxes here, but we'd have to look at something like how much area is shaded under the curve, and we usually have to look at it in an interval. It has to be, greater than a certain value or less than a certain value or between certain values. It doesn't really make much sense to talk about the probability of a particular value in a continuous distribution, because if you have an infinite number of values, the probability of any one of them occurring is always 0. Which is weird because in an interval it's not 0, but for a single value it is. A little paradoxical, it's just a mathematical thing. We don't really have to be too concerned about it, but just remember that with the continuous distributions, we always talk about the probability of a value being greater than or between A and B, or greater than and less than. So we never really talk about a particular value being equal to something. You also never see things like, well, why not look at probability of like x being less than or equal to a? We always talk about the probability of being x is strictly less than a. Well, again, what is the difference? If the probability of any value is 0, any particular value is being 0, then looking at whether x is less than that value or less than or equal to value won't be any different. In other words, the fact that this could be equal to will not change the probability. So we tend to only talk about the probability of things being strictly less than or greater than or between. Okay. So knowing that, the normal distribution is sometimes called the Bell distribution or the bell curve. And it's called that because it kind of looks like a bell, and it's perfectly symmetrical, meaning that if you kind of look at the middle and you kind of split it in the middle and you put up a mirror here, that the right side would look exactly like the left side, like a mirror image of it. The other thing about the normal distribution is in terms of things like we call central tendencies, the mean, median, and mode, they're all the same. They're right there at the middle, at the very peak. So the most frequent value, that's the mode, is equal to the middle value, where 50% is below and 50% is above, and it's equal to the average or the mean value. The mean value is sort of, if you put a teeter-totter here, that it would balance. You can see that if you put like a little fulcrum here, that it would exactly balance out the left side and the right side. So they're all identical, at least a priori or in principle. Now, there are two things that characterize a normal distribution, two parameters we call them. One is the mean, mu, which is the same as the median, the mode, okay, or the central tendency, and sigma, the standard deviation. So when we use these Greek characters mu and sigma, by convention, we really mean that this is the mean and that's the standard deviation. parameters in principle or a priori. That's what they are. We're not saying that we're calculating them based on data, but that's what in principle we think they are. And so the bell curve, or the normal distribution, is both symmetrical, has this middle part, which the mean, median, mode are all the same, and it has a characteristic that it's neither too flat, not like really going flat, like smushing down, nor too peaked. It doesn't have a tall peak. It's perfectly bell-shaped, is what we call it. And it has a range that goes from minus infinity to infinity, meaning that all possible values, the normal distribution can have any possible values. But of course, values that are far away from the middle tend to be very rare. Now, there's all kinds of different normal distributions. For any value of mu and sigma, any kind of mean and sigma, you get a different shape. You get a different, they're all bell curves, they're all normal distributions. They only vary, they only are different by the mean, the location of the middle, and the standard deviation, which is sort of the spread. You can see over here that the standard deviation is kind of like the belt. How wide is your belt? Sometimes we have tall and thin ones like this yellow one here. Sometimes we have long and fat ones like this pink one. So this one, pink one, would have a larger standard deviation. Its belt is wider, and this one would have a smaller standard deviation here. It means that the data is more variable for the pink one, and the yellow one is less variable. This one, these two have the same means. The center's at the same place. This one's mean is shifted over to the right. So that's the idea, is that by looking at these two parameters, we can determine any kind of normal distribution. The two parameters themselves determine the unique normal distribution. That's not our case for any distribution, but particularly just for normal distributions. So mu, or the mean, will shift it left or right, and sigma will increase or decrease the spread, making it taller or fatter. Because of that, we often will talk about the standardized normal. And the standardized normal is where the mean is 0 and the standard deviation is 1. Any distribution, any normal distribution, can be converted into a standard normal distribution, and any standard normal can be converted to any other distribution. There are arithmetic or formulas that will transform anything that's not normal, that's normal with mu and sigma, into the standard normal. So it doesn't matter whether we talk about the standard normal or we talk about another one with a certain mean and a certain standard deviation that's different than 0 and 1. They can always be transformed one into the other. And what I mean by transform is that we can always find the value. So when we talk about the standard normal, we mean that we often talk about the z-value or the z-score. We can look at how many standard deviations above or below 0 is a particular value. And that would be what we call the standard normal. Whereas if we look at it relative to a particular mean and standard deviation, that would be the regular normal. So to transform one to the other, or what we call the z-score, or the z-distribution, you could take, say, x as a random variable. That's a normal random variable that has mean mu and standard deviation sigma. And if we take that, whatever value that comes from that distribution, and subtract off mean, mu, and then divide it by the standard deviation, this shifts it over to 0 by spanning it over to and divided by standard deviation, sort of divides it so that the spread is 1. So this will make the z-score, or what is called the standard, convert x, which has mu sigma parameters, into the z, which has 0 and 1. It's really not that important. I mean, what happens is if we tend to look up things in tables, we usually get table values of z's, and then we have to convert them to the x's. That's usually where that comes into play. You'll see later on that we're going to use this in some of our calculations. The fact that we can take the standard normal to try to understand what percentage of the time something, a value, is bigger or less than, and then convert it to what it means to look at for our particular scenario at hand. So I already talked about this, that the standard normal distribution, again, is called the z-distribution, or the z-scores, has mean 0, standard deviation 1. And when we have values that are positive, that means I'm bigger than the mean. If I'm negative, they are below the mean. So that's what that means, and that you can see from the formula. For example, if I have x is a normal random variable with a mean of 100 and a standard deviation of 50, okay, then the z value for say something like x equals 200. Now 200 would be presumably a variable of that potential value of x with mean mu and standard deviation, mean 100 and standard deviation 50. If we take 200 and subtract off the mean 100 divided by 50, we get the value 2. In other words, this is 2 standard deviations above a 100. That's what the z-score means. It means we're twice the number of two standard deviations of 50 above 100 is how this is interpreted. In other words, this is also the value of 2 in the z distribution. So you can compare these quite simply, that if you have a normal distribution with, say, mean 100 and standard deviation 50 here, you look at the value 200 under the bell curve, you could see that in the z distribution that would be 0, and then the value at this point would be a z-score of 2, or around 2 standard deviations above 0. The distributions are, identical in some respects. They give you the same probabilities, for example. They just happen to be converted. So how do you find normal probabilities? We often need to do this. To find normal probabilities, we look at the area under the bell curve for that particular normal distribution. So let's just say we want to look at the probability that a normally distributed random variable x is between some value a and b. It doesn't really matter whether it's less than or equal to or less than. They're both the same, because again, the probability of any particular point is always 0. So essentially, if we're looking at the probability that x is some value between a and b, it's the same thing as looking at where is a, where is b, and looking at the area underneath the curve. So we want that total curve area. Some things are quite easy to think about. For example, if you want to look at what's the probability that my value is less than the mean, if I want to see the probability is less than the mean, we know that's always going to be 1/2. Why is it going to be 1/2? Well, you can see that it's symmetric, because the normal distribution is identical on the left side as on the right side about the mean here. Then the area under the curve here has to be 50%, and the area under the curve here has to be 50%. So if I go from minus infinity up to here, then that's going to be 50%, or 0.5, or 1/2. Of course, the area under the total curve between minus infinity and infinity has to be 1, all of it. The empirical rules for normal distribution says that if we know that something is normally distributed, then we kind of know approximately how frequently values occur with respect to the standard deviation. Let me give you an example of this. If we look at how often does a value that's normally distributed with mean mu and standard deviation sigma, how often is the value, or what is the probability that it's 1 standard deviation below or 1 standard deviation above? So I look at mu minus 1 sigma and mu plus 1 sigma. Again, I'm just looking at values that are 1 standard deviation below, values that are 1 standard deviation above. The empirical rule says that area underneath there is about 0.68, or 68% of the time values go between 68.26% to be more accurate, that values are within 1 standard deviation of the mean. So it's often frequently it's often convenient to talk about how many standard deviations, or if we know that something's normally distributed and we know what its mean and standard deviation are, then we can easily calculate its probabilities. And it tells us something about how that data behaves. So you can see, for example, that 68.26% of the time normally distributed values are going to be between 1 and minus 1 and 1 standard deviation. Okay, if you go 2 standard deviations below or above, or 4 standard deviations total, then you get 95.44%. That's most of it. And if we go 3 standard deviations, that's 99.73. That means that less than 1% of the time, I'm going to have values that are less than 3 standard deviations below the mean or greater than 3 standard deviations below the mean. That's because the area from here to here and there to there is less than 1%. Now, frequently we're going to use a table to look up a value for a normal distribution. Because the area under this curve is not easy to calculate, we usually will resort to a table that already calculates areas underneath the curve for the z-scores, or for the z-distribution, and then convert it back. If we have access to something like Excel, then there are functions and formulas that will calculate these things for us, and I'll show those to you later. So looking at the standardized normal table, let's take a look at this. I have an example. This is in our resources. This is an example of a normal distribution table. You see that they have a little diagram that says Z, and it has like a little shaded region, and it has these different things here. So how would we actually use this table to figure out what the area underneath the curve is, and then how would we use that to figure out probabilities for other normal distributions? Let's just say we want to find out, like, the standard normal distribution, mean 0, standard deviation 1. Let's look at the probability that Z is less than 2. In other words, how often are we less than 2 standard deviations above the mean? And we see that that's going to be 0.9772, or about 97.72. Again, that's the empirical rule. How would we figure that out? Okay, well, what we would do is we'd go to our table and look up where is Z equal to 2, and then go over to, so that would be, here's Z, go all the way down to 2, and then we go over into the chart and see that 20.00, so that's going to be 20000, or exactly 2, and we see that we get 0.972. Let's go take a look at that on our table. So you can see at our table here that this is telling us that when we have the shaded region here, it's saying that we're giving the probabilities from negative infinity up to the value Z. So it's coming from minus infinity up, or in other words, what's the probability that Z is less than, right? Less than this value here. So we go here, here's -6, and we keep going until we get over to 2, and here is 2 right here, and we want 2.000, so that's this value right here, and we see 0.9772. If we were looking at 0.2001, we might go over here and see that its probability is 0.9778. Close, but not exactly the same. So the general procedure for finding probabilities of any normal distribution, of course, is to kind of draw a sketch to show, what does it look like? Which area under the curve am I looking like? So I might want to find the probability that a normally distributed random variable x is between a and b. Okay, so what we do is look at where is A and where is B, try to get an approximate idea of what we're looking at here, and then translate those x values into z values, use the standard normal table. Let's take a look here. Let's say that x represents the time it takes in seconds for downloading an image from the internet. All right, and that might be normally distributed with a mean of 18 seconds and a standard deviation of 5 seconds. How would we find out that the probability of downloading an image from the internet, that's x, will take less than 18.6 seconds? Why are we choosing 18.6? I don't know. We just are. So we notice that 18 is the mean. So that means that's going to be right there in the middle, right? And so 18.6 is greater than 18, so it's going to be to the right. So we move over to the right here and say, well, maybe that's approximately 18.6. And we want to look at that where x is less than 18.6. So here's 18.6, and values over to this direction here are less than. Here they are greater than, here they are less than. So what we want is the area under the curve that starts from here all the way down to the end minus infinity. So how do we figure that out? Well, we will take a z-score for a look at 18.6. So we're going to, what is the z-score for 18.6? We take 18.6, subtract off the mean of 18, divide by the standard deviation of 5, we get a z-score of 0.12. In other words, this distribution here is exactly the same as this here. So with using the x's, I'm using the z's instead of the x's. Again, now we've converted the normal values into the standard normal values, and this z is less than 0.12 is something we can look up in our table. So we go to our table here and we go down and find, here's 0.1, right? And then we go 0.10, 0.11, and 0.12. And we see that 0.12 has a value of 0.5478, or about 54.78. So the area here, this red area, is about 55%. And you can see it's going to be more than 50% because 50% would be really at the middle part, right? And we're a little bit more than the middle part, so this seems about right. How will we find things like the probability that x is greater than 8.6? Well, the way we do that is we would translate this into a problem from something being greater than to something being less than. So making a sketch here, 8.6, okay, well, let's just say that we have something at mean 8 and standard deviation of 5. So 8's over here, 8.6 would be to the right of it, and now we want x is greater than 8.6. So that means we want values above 8.6, not below, but above. So we want this red area here. Again, we would translate this into a z-score, and then we would then look at it to a z-score to something to the left. So noting that the probability that x is greater than 8.6, we convert it into the z-score. We get a z-score of 0.12. Okay, and that was the way that we did it before. That's just doing where we subtract off the mean and divide by the standard deviation. Okay, going back to this here. And then notice that looking at something to the right, okay, where it's greater than, is the same thing as subtracting 1 from the thing to the left. And the way we look at that is that we know that the red part here, right, that the total curve is 1. The total area under the curve is 1. But if we look at the probability we want to go greater than this, right, we know that that plus what's left over has to be equal to 1. So in other words, if we take 1, which is the whole thing, and subtract off the red part, what we're left is the blue part. Now this blue part here is the probability that z is less than or equal to 0.12. So now we can look this up on our table. What is the probability of z is less than 0.12? We get that's 0.5478, like we saw before. 1 minus that would be then 0.4522, and therefore the red area here is about 45%. And you can see that's about right. It's going to be less than 50%. How about looking at a value of between two things, like between 8 and 8.6? Well, what we do is we convert that to a z-score and convert that to a z-score. Now, 8 is easy because the mean, right, is 8. Therefore, the z-score for 8 has to be 0. Because you can look at here, what is 8 minus the mean here is 8 minus 8, which is 0. So 0 divided by 5 is 0. Similarly, we already did this before. 8.6 minus 8 is 0.6 divided by 5 is 0.12. We get a 0.12 z-score. And now we want the probability that x with this mean and that standard deviation is between 8 and 8.6 is the same thing as looking at where z is between 0 and 0.12. We just translated it. Looking at a sketch here, you can see here's 8 and 8.6. We want this little slice here. So what we do is we convert this to two probabilities, looking that the value of p between 0 and 0.12 is the same thing as looking at the bigger side, which is the z is less than 0.12, minus the smaller side that p is greater than 0. So in other words, if we look at the probability that it's less than 0.12, that's all of this, that's going to be too much by this white region here. That white region here is where the probability is less than 0. So if we take this whole thing and subtract off this thing, the white part, we're left with the red part. And that's exactly what we hear. So now there's the bigger minus the smaller. So you figure what that is, you figure what that is, you look it up on the table, and you get 0.0478, about 5%. And you can see, once again, that red sliver looks about 5%. Does it make any difference whether I'm in the upper part or the lower part? No, same exact procedure. So let's just say we want to look at where x is between 8 and 7.4. So instead of the upper part and the lower part, you do the same exact process. Once again, convert that to a z-score. Now that's below 8. That's less than 8. So I'm going to get a negative z-score, right? That's a z-score of minus 0.12. That's 8. That's still going to be 0 because it's at the mean. And again, I just take the bigger side minus the smaller side. The bigger side is, well, at 0, that's all of this. That's going to be 0.5, we know. And then we subtract off this blue part here, leaving just the red part. Okay, 0.5 minus 0.4522, get about 5% again. Okay, how would we find x from a known probability? So of course, generally we can do the reverse. If we have a standard normal z with mean 0 and standard deviation 1, we can convert it to a normal distribution value with mean mu and standard deviation sigma just simply by multiplying that z-score by the standard deviation and adding the mean. This is going to be a very useful little thing, so you should pay attention to this. This is going to represent our basic model for expressing variability that occurs normally. And we would like to be able to say maybe with 90% of time a certain thing occurs that varies with mean mu and standard deviation sigma. We would use this formula to figure out what that is. So take an eye on this, as we're going to actually use this as part of our basic model in supply chain. So if we had to do that, what we'd do is, like, say, let's take an example that x is the time it takes in seconds to download an image file from the internet, and we know that x is normal with mean 18, standard deviation 5. What we might want to do is, like, okay, well, what value of x, given this condition that it normally varies with mean 18 and standard deviation 5, what value of x would be that 20% of the time the download times are less than x? It might be a question we ask. In other words, what would x have to be so that 20% of the time it's faster than that? So that's simply looking at the normal distribution here with mean 18 and standard deviation 5. Where we'd like to know what value here gives this shaded area to be 0.2 or 20%. Because again, these values would be less than, so this would be download times less than. One way we can figure that out is, of course, figure out what the z-score is. So if we look at what z-score gives 20%, then we can take that z-score and convert it to an x with mean 18 and standard deviation 5. And that's exactly what we would do. So we'd find out, okay, what z-score has 20%. So we go look at our table here, and we find that 0.2005 is pretty close to 20%, as close as we can get, I guess. And we see that that gives us a value of minus 0.84. So again, it's 0.8. This is the first digit, and this would be the second digit, 0.84. So a z-score of minus 0.84 gives a region that's 20%. So now all we need to do is convert this z-score into an x value whose mean is mean is 18 and standard deviation is 5. So we just use our formula here. So we just put 18 here, and we put 5 here, multiply that by minus 0.84, as you get right here, and you see that the equivalent value for in that normally distributed download time would be 3.8. So that means that 20% of the time, or 20% of the values, download times would be less than 3.8 seconds. Now, of course, we don't have to use tables. Most of the time, you're probably going to have Excel available to you or something like that. And you can, instead of looking up the values, you can calculate them directly in Excel. So it's a little more convenient. So if we were using Excel, we might have like let's just say we'd like to find, let's say we have the normal distribution where mean is 7 and standard deviation is 2, and let's say we want to find the probability that that normal value is less than or equal to, or same thing as less than, say 7, right? And we would like to find the z-score. You can use the standardized function. So standardize B8, so it's standardizing this, and with that mean, that standard deviation, just applies this formula in reverse. It says find z for this mu and that sigma given that x. And then we can also look at what the probability is for the normal distribution. If you want to find out what the probability that x is less than 7, let's just say, you could use norm dist. And norm dist is going to take a value, an x value, and it's going to take a mean and a standard deviation. And this thing over here, true, just means that it's the cumulative. It means it's the area under the curve. So there's a difference between the cumulative and the non-cumulative part. You almost never are going to use the non-cumulative. You're going to want the cumulative, because the cumulative tells you I want everything up to 7 here. So when you say true here, it's saying less than or equal to is what we're talking about. You can look at the probability that x is greater than by just simply flipping it over. So if you have an x value of 9, you can just flip over. You can still standardize the z value, and you can take 1 minus the normal distribution, and that's going to give you the value that's greater than instead of less than. So it's just, you just convert it yourself. If you want to see whether something is less than 7 or greater than 9, you just look at the probability that it's less than 7 plus the probability that's greater than 9. In other words, this plus that. Same thing for a range. If you have a range, then what you'd want to do is, you can look at the z-scores if you want, or you can calculate directly what you want using the norm dist. You get the probability of the the smaller one here is x is less than 5, and the probability of the larger one, and you take that minus that, and that gives you the range, the probability that x is between 5 and 9. And then you can do the reverse. Say you want to know what value of x gives you 10% or 0.1, or a probability of 0.1. You can just look at the norm's inverse. So if you have a standard normal, you just use norm inverse. If you have a non-standard normal, meaning that you have some mean and standard deviation, like here, B4 and B5, 7 and 2, you can use norm inverse. So norms with an S inverse means the standard normal. Norm in without the S means you're going to give it a mean and a standard deviation. So if you have the S here, it just assumes the mean is 0 and the standard deviation is 1. It's the same thing as saying norm inverse with a 0 and a 1 there. So that's the deal with using normal distribution. Of course, oftentimes we want to find out. So the question often arises that if you want to use the normal distribution, which is often convenient, that we need to be able to have some idea that the data, or that the thing that we're looking at, actually is normally distributed. And you may have forgotten how to do that. So one of the things we need to do is look at the characteristics of the normal distribution and see if they match our data, so that we can, if we model our data as a normally varying random variable or a normal distribution, that we are getting reasonably reliable results, or that there at least seems fairly reasonable that that's a good thing to do or to assume. Because remember that the normal distribution, just like any continuous distribution, is always going to be an a priori. That means in principle. The reality of it is that we're going to have data that's not necessarily going to be perfectly normally distributed, but we just want to know it's normal enough that we're going to get good results. So, and also, you have to think about that. Not everything is going to be normally distributed. It's a common error to just assume that things are normally distributed, but it's not. Even though quite frequently things are, they aren't always. So if you don't know in principle that something is going to be normally distributed, you don't have any reason to believe, then you can just look at the data empirically. It means you can observe it. So remember that the normal distribution would be something that looks bell-shaped. It's symmetrical, where the mean is equal to the median, and that you look at the empirical rules that certain percentages of the data is within certain numbers of standard deviations. And there's other things like the skew and kurtosis are nearly zero. So these are the things we would look at of our data. So if we could plot, we'd like to look at histogram of our data. And if we want to say that it's normally distributed, you'd say, well, does it look bell-shaped? Is the mean close to the median? Is 62% of the data within one standard deviation of the mean? You look at the interquartile range, is at 1.33, and is the skewness and kurtosis nearly zero? So those are the things we can look at if we're trying to determine normality, at least those certain first clues. Usually what we do is we just look at the data first. We might look at a histogram, a box plot, or a stem and leaf plot of the data and see if it has the characteristics that we're looking for in terms of symmetry and that it's bell-shaped and that kind of stuff. You also can compute the summary measures of mean, median, mode and see if they have similar values. You can look at the interquartile range and see if it's about 1.33 of that times the standard deviation. Is the range approximately 6 standard deviations? Because remember, almost less than 1% of the data is going to be outside of 6 standard deviations. So you look at the range of the data and see if it's like that. The skewness and kurtosis between -1 and 1, because that's what we'd say is closest to 0. The one warning is that when you look at data, oftentimes there are outliers or data that kind of is unusual or unexpected, and there could be a variety of reasons why something is an outlier. It could just be coincidence, or it could be because of bad measurement or bad data input or something like that. So you have to be careful that an outlier will mess these things up, and you don't want to be skewed by something that would be necessarily something that you would not normally pay attention to. So if you're going to use the empirical rule, you can look at whether how much of the data fits within how much of the standard deviations, and that's actually the most important characteristic of the normal distribution when you're calculating things with it, is that basically we understand how much data fits within a certain number of standard deviations, because that's what's going to make our approximations unreliable if this empirical rule doesn't hold. Quite frequently people will also look at a normal probability plot. So a normal probability plot is where they plot the quartiles or the quantiles of the normal distribution with the quantiles of the data, and if it looks like a line, then you can say it's approximately normal. So for example, here would be the z-scores. Okay, those are going to be the number of standard deviations above and below the mean, and then we look at the quartile for a normal distribution here, and then we would plot what the actual quantiles are. And again, these quantiles would be, if it was normally distributed, this is what we would expect, and this is what we actually get. And so if they meet, they'll be on a line here. They're about the same. And so the more closely that this looks like a line, the more normal we would expect it to be. You see certain patterns that are pretty common, like if you see the data, if you see the quantile plot bends over like this, it would be skewed in one direction, either left or right. And if you see something that's kind of flat, like it's not bell-shaped, you see kind of an S shape like this. So again, this is not the end-all and be-all, but again, if you look at a quantile plot, you can see if it looks kind of more or less like a line. And again, if there's a few points off, that's not really what we care about. We look for the general trend. You can also look at things like, let's look at a box plot. Let's take an example here. So let's just say we have some bond fund returns, and we would like to see whether they are approximately normal distribution. If we look at a box plot here, the box plot represents the 5-number summary of it's the minimum value, the maximum value, which means the whole whiskers here would represent the range, and we'd want to see is that sort of 6 sigma. We look at the first quartile, which means this is 25% of the data is less than this, and the median, or the second quartile, 50% is less than this, and the third quartile, 70% is less than that. So what we're looking for is we kind of want to see that this box here, the middle box, which this here is the interquartile range, is pretty close to the middle of this range here, because if it's not, it would be skewed. And you can see this is, the middle would be right around here, so it's over to the left a little bit, which means that the distribution is a bit skewed to the right. I know it sounds weird, but if it's moved to the left, it's actually skewed to the right. That's what that means. Another way of looking at that is you see that this whisker here is a bit longer than that whisker, and those should be approximately equal. Now, as the median should be right in the middle, and that would be the same for the mode and for the mean. The other thing we're looking at is how small this box is. This box should be approximately a third of the size of the range here. So we have this whole range here, and if we can fit just about 3 in there, then we'd say that the distribution is neither too peaked nor too flat. It has to do with how bell-shaped it is, or the kurtosis. And you can see here that we actually can fit several more of these boxes in 3. You kind of can get 1, 2, 3, 4, 5. So this is actually fairly peaked. It's pinched. It means that there's more. It's more narrow and taller than we would expect for a normal distribution. If it were really big and wide here, then a lot of the data would be spread out through the range, and that would be more flat. So you can see, for example, in the descriptive summary here, let's take a look that we said it's skewed to the right. Skewed to the right means that we'd have a positive skew value, and that it's kind of pinched here. This box is too small, which means it would have a positive kurtosis. And here we are looking at the skewness. It's 0.9, so it is positive. And look at the kurtosis. You can see it's very peaked. Generally speaking, we look to see at the skewness or kurtosis that if they're sort of between, both of them are between -1 and 1, then we say, it's close enough. It's not too skewed. It's not too peaked or flat. In this case, our data seems to be fairly peaked, and we'd probably want to know why before we would look at things. But we might take a look at some of the empirical values here and see, well, how far is the interquartile range? How much data is between 1% and the other, one value and another. Whereas you see, look, 73.91% of the observations fall within standard deviation. If it was normal, we'd get 68.26. So you can see this is a bit off. So once again, you can see why you want to check that your data is normally distributed, or at least that meets the characteristics, because if it doesn't, then if you assume that it is, like this value here is going to, if we assume it's normally distributed and we calculate, say, normal probability values for this, we're going to that this is the kind of things we would get when actually it's this. So our values would be inaccurate or way off. Okay, and again, you could continue looking at the different how many standard deviations give you how much data. And again, as we get farther out, it's not too bad. But that's mostly because the data tends to be concentrated in the center because of the high kurtosis. And again, I looked at the skewness and kurtosis, and even though the skewness is okay, we expect our kurtosis to sort of be between -1 and 1, and it's not. Looking at the quantile plot, or the normal probability plot, you can see that over here it's pretty much a line here. This is really not a big departure, but then you see it kind of goes up like this, and it shows that this is skewed to the right a bit. Okay. What doesn't really appear is that the kurtosis is very high. So what we would conclude with mutual funds is that returns are skewed to the right, and that kind of makes sense because returns probably tend to be more positive than they are negative, and we have things like returns have values that more values within one standard deviation than expected because it's concentrated around the mean more than you'd think if it was normally distributed, and etc. We look at the various different characteristics that don't add up to assuming that the data that mutual fund returns are normally distributed. We probably not want to rely on that assumption. Okay, so that's it, and I'll see you in class, and we'll show you how we're going to apply some of these concepts